Alright, in today's lecture, we'll be going over content for Chapter 9, which is covering quantum mechanics. And so far in class, we have covered a couple of different things: photoelectric effect, Bohr model, and the Heisenberg uncertainty principle. And what that leads us to right now is our understanding of quantum mechanics, and what we're going to be using is some mathematics to get to the particle in a box model. So for the discussion of the particle in a box model, we are going to use mathematics that are commonly used to describe a vibrating string. So math is described by that of a vibrating string and linear differential equations. And we'll get in to understand that the same mathematics that helps describe a vibrating string can also help to describe a vibrating or oscillating particle, which we know as an electron or particle wave. So let's start off with our classic wave equation. In the classic wave equation, we can imagine that we have the beginning and end of a guitar string, and we have some sort of vibration that is traversing through the guitar string as we go from the beginning to the end of the guitar string, from 0 to L. And we would describe the position of this moving wave as a function of x along our guitar string. Now what we're going to do is describe this vibrating string through a linear differential equation, and we're going to say that we need to account for the function as space and time. And let's also remember that the description of what's going on with this wave is going to be some function u as a function of position and time, which is what we have right here. And so we're going to have our partial differential equation with respect to time equal to 1 over the velocity of the wave squared, then a partial differential with respect to time as well. Now the boundary conditions of this linear differential equation are going to be as such. Boundary conditions are the description of what our function has to be at the beginning and end of our guitar string. In this particular case, our function u at 0 and some time t must be equal to 0. So that's the amplitude that we have there at the beginning of the guitar string. And at position L, the end of the guitar string must also be equal to 0. I'd like you to see the parallel with this for an electron at the beginning and end of the molecule, whatever that molecule happens to be, such as benzene. Now, in order to do work on this linear differential equation, we're going to do three things. One, we're going to take our wave equation, our description of the behavior of the wave. We are going to do a separation of variables. Step 3 is we're going to apply the boundary conditions. And 4, we are going to solve for our linear differential equation. And so let's go through these steps one by one and see where this leads us. One aspect that we should highlight, and is a very big take-home message, and that is the solutions to linear differential equations are linear functions. And this is a big deal. Of the form of y equals mx plus b. So when we have our linear differential equation like that for our vibrating guitar string, once we have some solutions, the solutions themselves will be another function. And in this particular case, it will be that which has some slope as well as a y-intercept. And usually we see this as a y equals mx plus b form. And you'll notice that we've seen this multiple times within physical chemistry, where we do some sort of transpose on a particular phenomenon to then yield our linear equation. So let's go through step one. Separation of variables. And with the separation of variables, what we're going to do is we're first going to create a new function. And this new function is going to be u of x of t equals x of x and t of t. And we're going to substitute this into our wave equation to yield partial differential with respect to x and x and t of t with respect to space equals 1 over velocity squared, our second partial versus t of x of x and t of t with respect to time once again. And let's recall that that 1 over x squared is the velocity of our wave. So the next step that we are going to be doing is rearranging this function mathematically. And what we want to do is pull outside all of our partial derivatives and be able to separate all variables, all functions on one side. So we've got our t of t, partial derivative with respect to space, 1 over v squared, x of x with the partial derivative with respect to t of t as a function of time. We are then going to divide this function by u x of t, which you'll recall is equal to x of x, t of t, to then yield a new function, which is 1 over x of x, partial derivative of x of x with respect to x, 1 over the velocity squared, 1 over this function t of t, second partial derivative with respect to t, and this is in time. Now let's look at this. One of the important things now that we'll notice is that we have x on one side, on the left-hand side, and we have functions of t on the right. And let's keep moving along and see what we do now. Okay, and let's write that down. We now have an equation whereby the functions of x and t are separated, and we can now describe it as 1 over x of x, partial second derivative with respect to x as well, equals k, some constant, equals 1 over t of t, partial derivative with respect to time as well. And this is important, and the next thing that we're going to be doing is focusing on this behavior and how the function will respond when this constant k is 0, positive, or a minus value, and we'll be doing that shortly. So now we've got our function, and we'll focus on the function with respect to space. And we've got our partial second derivative with respect to x is equal to k. And now what we're going to do is we're going to multiply by both sides by x over x over 1. And you'll notice that that portion of the function will cancel out. And then we're left with the partial second derivative with respect to space equals k x of x. We will then move our constant with our function x of x to have it equal to 0. And now we'll have our partial derivative with respect to space minus k x of x. This is where we are going to do most of our work right here, and we will then modify our values of k, this constant, and we'll get into that shortly. So the equation for x of x is essential for the time-independent Schrodinger equation, and so we'll focus mostly on the function as a description of its position along the wave, and it's going to be important for us because we're not going to worry about where our wave function is in time, more along space within a molecule itself. So we've got our equation with respect to space, k x of x is equal to 0, and we're going to go ahead and we're going to integrate and assume that k is equal to 0. And when we go ahead and integrate this function from 0 to x, from x of x with respect to x equals 0, we are going to have some solutions. The solutions from this function, x of x, are equal to a1x plus b1. You'll notice that we have a linear function here. And a and b are integration constants. And if we apply, and this is important, if we apply our boundary conditions, and remember that the boundary conditions are telling us about the amplitude of the function at a certain position. And if we apply our boundary conditions, we find that both a and b must be equal to 0. And this gives us a trivial solution. Well, what does that mean? Well, if we have x of x, 0 times our function x, plus 0 at all of those positions as a function of x is equal to 0. Well, that basically means that at all values of x, the amplitude of the function is equal to 0. And so basically, you would just have a flat line along your guitar string regardless of position. And while this is mathematically a solution, it is extremely boring and is something that we need to disregard. It is a trivial solution. So let's move on and see what happens when we change the value of k. So now, let's see what happens when k is a positive value. And we're going to substitute this in to our x of x function. And at this time, we're just going to say that our new function is going to be y of x to help differentiate between our first and second example. Again, we've got our partial derivative with respect to x minus k squared y of x equal to 0. We know that every solution to a linear differential equation of this form is y of x is equal to e to the alpha x. This new equation, which helps to describe the behavior of our linear differential equation, e to the alpha x, and alpha is a constant, and we'll get into the description there. And we're going to substitute this in to our past equation to yield alpha squared minus k squared y of x is equal to 0. Now, y of x being equal to 0 is, again, a trivial solution. Therefore, we need to find a solution somewhere of alpha squared minus k squared equals to 0. And what we want to do is solve for this equation. And so you'll notice if we rearrange it, we'll get alpha squared equals k squared. And if we then solve for alpha, you'll notice that our values for alpha will be equal to plus or minus k. So right now, for our constant alpha, we have two solutions. This solution for our equation then becomes y of x is equal to our integration constant, e to the kx plus b sub 1 e to the minus kx. Now let's take a step back to make sure that we have our math aside and our proof for what we just derived. So we've got our second partial derivative with respect to our function y of x minus k squared y of x equal to 0. And let's recall that y of x is e to the alpha x. And so we're going to substitute in our y of x to get alpha squared e to the alpha x minus k squared e to the alpha x equals 0. We're going to then factor out that function to yield alpha squared minus k squared e to the alpha squared equals 0. And you'll recall that this e to the alpha x is in and of itself y of x, and that's how we got alpha squared minus k squared y of x equals to 0. And we ended up just pushing through and then solving for our value for alpha, which we found to be plus or minus k. And let's keep moving forward. So, as a brief recap, when k equals 0, we've got some function x of x, which is equal to a sub 1x plus b sub 1x. Remember, a1 and b1 are some sort of integration constant. And then when k is larger than 0, our function y of x is equal to a sub 1 e to the kx plus b sub 1 e to the minus kx. Now, let's consider the situation where k is less than 0, and this is where things will get a little bit different. Now, one thing that we want to recall is that some differential equations have solutions with oscillatory functions. And the word that should ring true to your ears is oscillatory. So, when k has negative values, we're going to start off with our function with respect to space plus y of x equals to 0. And you know that y of x in this respect is equal to e to the alpha x. And we're going to substitute that into our equation to yield the partial second derivative with respect to space, e to the alpha x plus e to the alpha x equals 0. And once we've gone ahead and done our partial derivative, and you'll notice that we are going to keep pulling down our alpha during each one of the partial derivatives with respect to space, we're going to have alpha squared e to the alpha x plus e to the alpha x equals 0. Let's go ahead and then factor that function, and we'll get alpha squared plus 1 e to the alpha x equals 0. And of course, once again, we don't want to have e to the alpha x equals 0. That would be a non-trivial answer. So what we're going to do is focus again on this portion of the function where it's alpha squared plus 1 equals 0. That means that we are solving for alpha. So alpha squared equals negative 1. We take the square root of alpha and find out that the values for alpha must be the square root of negative 1. The square root of negative 1 you know as I. And so we now have solutions for our constant alpha, which are the plus and minus value of I. Now we want to go ahead and substitute this into our oscillatory function, and now what we yield is y of x is equal to c1 e to the ix plus c2, and remember that c2 and c1 are just integration constants, e to the minus ix. Now what's interesting is that these imaginary numbers, remember that I is imaginary solutions, can be expressed using Euler's formula. And it's very elegant. What Euler's formula shows is that e to the I theta is equal to cosine theta plus or minus I sine theta. And you may be saying, Professor Wolcott, how did all of a sudden we get theta inside of here? Just imagine now that our value for theta is going to be something equal to x, because we're looking at an oscillatory function. And we know that oscillatory functions can be defined by some value theta, the degrees in which an oscillatory function is moving through this oscillatory wave. And so now what we want to do is, if we substitute into y of x equals c1 ei to the x plus c2 e to the minus ix, we're going to get a new function, which is going to be represented by c sub 1 plus c sub 2 cosine of x plus sine of x I c sub 1 minus I c sub 2. And this can be further simplified. We simplify it by saying c1 plus c2 is just equal to c3, and our constant for our imaginary number c1 minus c12 is now c4, and this yields our function y of x is equal to c sub 3 cosine of x plus c sub 4 sine of. Okay, now we apply our boundary conditions, and you'll recall that our boundary conditions are basically saying that the amplitude at the beginning and the end of the string must be equal to 0. So y of 0 must equal 0. Just keep that in the back of your head. Okay, so if we have y of x equals c4 sine of x, well, that holds true then. And we can also have, because we know that the cosine of 0 is equal to 1. So that is not going to allow us to be able to work within the boundary conditions. And so we can go ahead and make sure we have our little math aside over here, that the sine of 0 is equal to 0, cosine of 0 is equal to 1. So we need to stay within those confines of the boundary condition. And that eliminates our cosine function and takes it to 0. And so that's where we want to make sure that we have a connection. And we can also say that y of x is equal to some constant. That's all c4 is. It's just a constant. So it's equal to a sine of x. Well, that looks pretty good to us. That description of y of x is equal to a sine of x. Okay, that's a sinusoidal function with respect to x. And we could also go ahead and put it with respect to time. Well, let's just say we do that. And so we have some function with respect to time is a sine omega t. And you'll recall that this is the same sort of a function that we would use for a sound wave or light. And omega right there, omega is our angular velocity, and the angular velocity is equal to the frequency times 2 pi. So now we've come full circle, wherein the solution of our wave is sinusoidal. Okay, so we found that the general solution, or a universal solution, to the wave equation that we've been doing work on is a superposition of normal modes. And when I draw a normal mode, you'll say, oh, I get what a normal mode is, but we'll hold on. This general solution can be described with this cosine portion of the function and our sinusoidal portion of the function. And I'm throwing some value beta right there, and I'll get into beta. This is a parameter that we're going to play with shortly, and it's going to describe the length of the string. To that general solution, we apply our boundary conditions, which say that at x equals 0 must be equal to 0, and that implies that a must be equal to 0. And so that also means that x of the length of the string is equal to b sine beta times the length of the string equals 0. And b being equal to 0 is uninteresting. So now what we want to consider is the sinusoidal function. So when is the sine of beta L equals to 0? Well, this is going to happen when we have sine of theta equal to 0. And if we were in degrees, that would be when theta is equal to 0, pi, 2 pi, so on and so forth, 3 pi. And so we have this oscillatory function that's coming out. And so we would say that beta L is equal to n times pi, where n is equal to 1, 2, 3, 4. And this should be eerily familiar. N is similar to what we saw in the Bohr model and can be akin to our primary quantum numbers. And so let's keep that in the of our head in the way that we think about how these mathematical solutions help describe an electron. So we take that information and we say that our function x of x is equal to b sine of n pi x over L. Remember that x is our position along the string, and L is the length of the string, or the length of a molecule. A similar solution can be obtained as well. And so what we could also say is that omega sub n is equal to beta v, v being our velocity, is equal to n pi, the velocity, divided by L. And we combine our function for x of x and t of t. So we have a description of both time and space, and we get this monstrous function, which is now our wave equation is as a function of both space and time is equal to b sine of n pi x over L times d cosine omega n t plus e sine of omega sub n t. And it's just some monstrous description of our wave. And if we sum over all values of x and t, we'll get u x of t summing from n equals 1 to infinity a sub n cosine omega sub nt plus phi, and you'll notice that that looks like a phase shift, and that's what it is, times sine n pi x over L. And again, our solutions with n are going to be integer values 1, 2, 3, so on and so forth. So what can we get from all of this? This is crazy. Well, what we've just derived are the normal modes of a vibrating string. And so this harmonic motion of the string is going to be a function of n is equal to omega sub n. 2 pi is equal to velocity times that integer value over 2 times the length of the string. And how do we get that? That's because our angular velocity is equal to n pi times the velocity over the length of the string itself. And this looks like, when we actually draw it, as something very, very elegant. These normal modes look like this. We've got our guitar string, and when n equals 1, the normal mode, when n equals 1, is a fundamental mode. And you'll notice that the amplitude at the beginning and the end of the string is equal to 0. The fundamental mode is also known as the first harmonic. When n equals 2, our normal mode has this shape, and this is our second harmonic, or first overtone. And if n equals 3, we'll have a wave that has these features. Again, the amplitude, our boundary conditions are equal to 0 and 0 at the beginning and the end of the string. Remember that this is 0 at the beginning of our string, and L the end. And this is our third harmonic, or second overtone. Now what we've done here is laid a framework. The framework we've just created can now be applied to the description of an electron. So let's get that. The same type of mathematical equations which describe a vibrating guitar string in its normal modes are now going to be used to describe the behavior of an electron, but now an electron can be known as a particle wave. And we'll get into that in our next video.